Hello everyone. I'm going to be learning vectors again. I'm going to continue studying the Calculus
Hello
3 book.
everyone. I'm going to be learning
And
vectors
I will try
again.
to finish the last two
I'm going to
chapters,
continue
or
studying
maybe at
the
least Calculus
Hello
3 one
everyone.
chapter.
I'm going to be learning
And
vectors
I will
again.
try to finish like I tried to do in
I'm going to
every
continue or maybe at least
stream.
Calculus 3 one chapter. I'm going to be learning I will try to finish.
Hold on. Like I tried to do in
I'm going
every
to or maybe at
stream.
least Calculus 3 one chapter. I will try to finish.
Hold on.
Like I tried to do in every stream. Calculus 1 chapter. I will try to finish.
Hold on.
Like I tried to do in every stream. Calculus 1 chapter. I will try to finish. Hold on.
Okay, so wait. Sorry. Alright. So last time I was studying vectors in space. We did equations of lines and planes in space. Let me just do a quick review and then we'll start the next chapter. So two non-zero vectors are parallel. We claim there must be a scalar k such that u is equal to kv. So u kv implies u and v are parallel. And if you want to represent a line, we do it with this equation. So x, y, z is equal to r0 is some fixed point. Hold on. Yeah, r0 is the fixed point and v is the vector which is the same direction as the line. x0, y0, c0 plus it with t, a, b, c. So point on a line and then this one same direction as line. And then the next part was, yeah, this is for line segment. The distance between a point and a line would be, hold on, the magnitude of the cross product divided by the magnitude of v. So the magnitude of the cross product gives a parallelogram, the area of a parallelogram. We are dividing it by base v because the magnitude of v times this gives the area of the parallelogram. It's this here. So the closest distance from a point to a line would be P and M. Oh, sorry, P and M is this, right? P and M cross product V gives the area of the parallelogram. PM cross V divided by, actually it would be easier if I write it like this. D cross a magnitude of V. And then, so Here's a line. Here's a point. And then this would be the shortest point. Let's choose, yeah. And then this would be the parallelogram. Let's choose blue. And then this is point M. Actually, no. This is point, yeah, this is point M. This is P. And this is D. This is 90 degrees. And V is point here. Let's see. Vector V. Point P. And then vector, okay. So take this. Let's this is vector V. So area of the parallelogram. So this D is the shortest distance. The area of a parallelogram is the height, which is D, times it by V. Actually, V is yeah. So the cross product is the parallelogram formed by P, M, and V. So what's the next thing we learned? The relationship between the lines, whether they intersect or not. Equations for a plane. Yeah, for the equation of the plane, N dot PQ has to be 0. P is, I think P is a fixed point, and Q is any point on the plane. So all points X, Y, Z, you choose any point X, Y, Z, that would be point Q. So Q minus P dot N should be 0. And that defines all points on the plane. So let's say N is defined by A, B, C dot P minus Q. So let's say Q is X and P is X0, Y minus Y0, C minus C0. So the dot product should be 0. So I can define it like this. When you're doing dot product, you just multiply them element wise. But I'm just putting all the minus on one side. Zero, Y0, less it with C0. And yeah, we can write this as, sorry, this is CY, CZ actually, plus D. So if you have a 3D graph like this, I'm just making an axis. Drawing in 3D is very difficult. If you have a 3D plane, I don't know how to, let's say, I mean, I can draw shapes, right? Okay. Anyways, let's just do it like this. Does this make sense? Anyways, if you basically if you change the ABC vector, so you have a choice between ABC. So the plane is defined by ABC and this x0, y0, z0. So ABC is the perpendicular vector. If you change that, the gradient of the plane gets changed. So if you view it from the side, so let's say viewing it from one side, uh, so if we change ABC, the perpendicular vector, which is like out here, changes. So changing ABC would change the gradient of the plane. And then changing this D over here, or changing x0, y0, z0 would change like the position of the plane. If we change D while keeping everything else, while keeping the ABC same, it's going to change the position of the graph. Position of the plane, I mean. Okay, let's just, is there anything? And then they did cos theta, because theta is same here and here. They're using the perpendicular vector to find the theta between the planes. So from the dot product, we learn that n1 dot n2, the magnitude, the scalar value of this, or the absolute value of this, divided by the magnitude of each, would give theta, cos theta. We can use that to find the angle between the planes. So going to the next chapter. The first surface we will examine is the cylinder. Although most people immediately think of a hollow pipe or a soda straw when they hear the word cylinder, here we use the broad mathematical meaning of the term. As we have seen, cylindrical surfaces don't have to be circular. A rectangular heating duct is a cylinder. Uh, as is a rolled up yoga mat and the cross section of a spiral of, of which is a spiral shape. In the two-dimensional coordinate plane, the equation x squared plus y squared equals 9 describes a circle centered at the origin with radius 3. In three-dimensional space, the same equation represents a surface. Imagine copies of a circle stacked on top of each other on the z-axis, forming a hollow tube. We can then construct a cylinder from the set of lines parallel to the z-axis passing through x squared plus y squared equals 9 in the xy plane. Or because the z isn't defined, any z would work, right? A set of lines parallel to a given line passing through a given curve is known as a cylindrical surface or cylinder. The parallel lines are called rulings. A set of lines parallel to a given line passing through a given curve is known as a cylindrical surface. Well, I think what they mean is if I draw a straight line from here to here, and then I draw a straight line from here to here, let's choose red. No, this is a highlighter. So if I draw a straight line here, that's not straight. And if I draw a straight line here, and another one behind also. Basically, all these lines are parallel. I think this is what they're calling rulings. In three-dimensional space, the graph of the equation c is equal to x cubed is a cylinder, a cylindrical surface with rulings parallel to the y-axis. Oh, so they have a completely different definition for cylinder. So graphing the cylindrical surfaces, x squared plus z squared is 25. So there's a circle on the xy plane. We can stack those circles on the y-axis. Here they have z is equal to 2x squared minus y. Okay, it looks like that. Wait, a set of lines passing through a set of lines parallel to a given line passing through a given curve is known as a cylindrical surface or cylinder. Or if you choose one line and a set of lines parallel to all of those lines is a cylinder, no matter what the shape is. So in this case, the line would be like in this direction. So this shape gives a set of lines that is parallel to a line that is parallel to, let's say, this line. Okay. When sketching surfaces, we have seen that it is useful to sketch the intersection of the surface with a plane parallel to one of the coordinate planes. These curves are called traces. We can see them in the plot of the cylinder in figure 2.8. The traces of a surface are the cross section created when the surface intersects a plane parallel to one of the coordinate planes. Wait, hold on. The traces of a surface are the cross sections created when the surface intersects a plane parallel to one of the coordinate planes. Also, the intersection of the y-axis would give this shape. So that's a trace. So it can be any surfaces, right? Not just cylindrical. Traces are useful in sketching cylindrical surfaces for a cylinder in 3 dimensions, though only one set of traces is useful. Cylindrical surfaces are formed by a set of parallel lines. Not all surfaces in 3 dimensions are constructed so simply, however. We now explore more complex surfaces, and traces are an important tool in this investigation. We have learned about surfaces in 3 dimensions described by first order equations. These are planes. Some other common types of surfaces can be described by second order equations. We can view these surfaces as 3 dimensional extension of the conic sections we discussed earlier. We call these graphs quadratic surfaces. So, okay, they have x squared, y squared, and z squared. X, y, x, y, z, then x, y, z, and then an empty k. An ellipsoid is a surface described by an equation of the form, this form, set x is equal to 0 to see the trace of the ellipsoid in the yz plane, or it gives an ellipse. To see traces in the xy and xz plane, set c is equal to 0 and y is equal to 0 respectively. Notice that if a is equal to b, the trace in the xy plane is a circle. Similarly, if a is equal to c, the trace in the xz plane is a circle. Okay. This is what ellipsoid looks like. The trace of an ellipsoid is an ellipse in each of the coordinate planes. However, this does not have to be the case for all quadratic surfaces. Many quadratic surfaces have traces that are different kinds of conic sections, and this is usually indicated by the name of the surface. For example, if a surface can be described by an equation of the form then we call that surface an elliptic paraboloid. The trace in the xy plane is an ellipse, but the trace in the uh, xz plane and yz plane are parabolas. Oh, so cutting from here, you see an ellipse. Cutting from the side, we would see a parabola. So if it's a circle, it's an ellipsoid. If it's a parabola, an elliptic paraboloid. 17 standard quadratic surfaces can be derived from the general equation. The following figure summarizes the most important ones. So an ellipsoid, so in each plane it's an ellipse. We have hyperboloid of one sheet, and then there's also hyperboloid of two sheets. So it gives an ellipse on one of the plane and hyperbola on the other two. Same thing here. Wait. And then we have an elliptic cone. And then we have an elliptic paraboloid. Then we have a hyperbolic paraboloid. Okay, wait. If y is equal to q, a hyperbola. If x is equal to r, a hyperbola. Well, what do they mean by x is equal to r? This chapter was mainly about introducing more shapes. It wasn't really about vectors. I mean, it is about vectors, but it's only about three-dimensional shapes. Okay, I think I will do these questions off stream. Should I do at least one of them? Identifying equations of quadratic surfaces. Identify the surfaces represented by the given equation. So we have x squared, y squared, and z squared. Let's see. We have plus on each side, right? Mm, so that's an ellipsoid. We have x squared, x, y squared, y, and z. Identify the surfaces represented. Hmm. Let me think. If y is 0 and z is 0, you get a parabola in the... No, never mind. It isn't there an answer key? Wait, hold on. I'm just looking for the answer key. I just opened the other file. And what is this? 2.6, right? So we have 2.1, 2.3, 5, 6. The surface is a cylinder with rulings parallel to the y-axis. This is, oh no, wait, this is from an example. The x, y, z terms are all squared and are all positive, so this is probably an ellipsoid. However, let's put the equation into standard form for an ellipsoid just to be sure. We have this dividing by 144 gives this. So in fact, so this is in fact an ellipsoid centered at the origin. You first notice that the z term is raised only to the first power. So this is either an elliptic paraboloid or a hyperbolic paraboloid. For an elliptic paraboloid, the z is only to the first power. But there's also plus 25. Does that do anything? This is an elliptic paraboloid centered at 1, 2, and 0. Yeah, we'll just do some of these upstream. Okay. Cylindrical and spherical coordinates. The Cartesian coordinate system provides a straightforward way to describe the location of points in space. Some surfaces, however, can be difficult. Some surfaces, however, can be difficult to model with equations based on the Cartesian system. Wait, hold on. Okay. We have, when we expanded the traditional Cartesian system from 2 dimension to 3 dimension, we simply added a new axis to the model to model the third dimension. Starting with polar coordinates, we can follow this same process to create a new 3 dimensional coordinate system called the cylindrical coordinate system. In this way, cylindrical coordinates provide a natural extension of polar coordinates to 3 dimension. In cylindrical coordinate system, a point in space is represented by the ordered triplet r, theta, and z. R theta are the polar coordinate of points projection in the xy plane. Z is the usual z coordinate in the Cartesian coordinate system. So x, y, and we have z. I think for the spherical coordinate, they use another angle for the z direction. The rectangular coordinates x, y, z and the cylindrical coordinates r, theta, z of a point are related as follows. So x is r cos theta, y is r sin theta, z is the same. R square is x square plus y square. Then tan theta is y over z, and then z is the same. Let's consider the differences between rectangular and cylindrical coordinates by looking at the surfaces generated with each of the when each of the coordinates is held constant. If c is constant, then in the rectangular coordinates, surfaces of the form x is equal to c and y is equal to c or z is equal to c are all planes. Planes of these forms are parallel to the yz plane, the xz plane, and xy plane, respectively. So in cylindrical coordinates, surfaces of the form r is equal to c are vertical cylinders of radius c. Okay. Surfaces of the form theta is equal to c are half planes at angle c from the x-axis. Wait, this one is kind of confusing. So theta is fixed. Wait, hold on. So theta is fixed. Let's say theta is fixed to this. And then if we define it for all r and c, we get half plane. Yeah. Oh, that makes sense then. And then z is equal to c, the same thing. Converting from cylindrical to rectangular coordinates, plot a point with cylindrical coordinates and express its location in rectangular coordinates. Okay. So we have 2.6. Plot the points with these cylindrical coordinates. So 4, 2 pi over 3, and then minus 2. This is the cylindrical coordinate. In the cylindrical coordinate, we have r, theta, z, which is x, y, z here. X is r sine theta. Wait, no, wait, cos theta, I think. Yeah. Y is r sine theta, and then z is the same. So then we have 4 times cos. Now let me just do it here. 4 times cos 2 pi over 3. It's minus 2. This is a minus 2. This is a minus 2. Then we have sine 3.46. Minus 2 to root 3. 8 2. Yeah, it gives 3.46. And then converting from rectangular to cylindrical coordinates is basically the reverse. Identifying surfaces in the cylindrical coordinate system. Describe the surfaces with the given cylindrical equation. I already saw the answer. X is equal to pi over 4. I mean, theta is equal to pi over 4. When theta is held constant while r and z are allowed to vary, the result is a half plane. So theta is pi over 4, but it's only describing this part of the plane, right? But r can be negative also, right? So we can have the whole plane technically. Wait, why do they say half plane when r is allowed to be negative? I looked at the other answer. R square plus z square is equal to 9, which is basically. Wait, hold on. Wait, over here, r square is plus z square is equal to 9. So r square. Oh, r square is only in the xy plane. And then z square goes directly above. That is equal to 9. So yeah, it describes a sphere. I got confused for a second. And then what's the last one? Z is equal to r. Defines this. To describe the surface defined by the equation Z is equal to r, it is useful to examine traces parallel to the xy plane. For example, the trace in plane Z is equal to 1 is circle r is equal to 1. Trace in plane Z is equal to 3 is circle r is equal to 3, and so on. Each trace is a circle. As the value of Z increases, the radius of the circle also increases. The resulting surface is a cone. This isn't exactly a cone, it's more like the ellipsoid. What was it called? The parabola ellipsoid. It's not exactly a cone. The intersection is an ellipse. Spherical coordinates. In the spherical coordinate system, a point P in space is represented by the ordered triplet uh, phi, theta, rho, theta, and phi. Rho is the distance between P and the origin. Isn't rho like like r? Theta is the same angle used to describe the location on the cylindrical coordinates. Phi is the angle formed by the positive z-axis and the line segment OP, where O is the origin. So now we have two angles, one from the x-axis, the other one from the z-axis. I thought the other angle is from the xy plane. So we have rho, theta, phi. Rho is the distance. R is the bottom one. Z is this one. So converting among spherical, cylindrical, and rectangular coordinates. So point X over here is defined by r cos theta. But wait, we would also need, hold on, r is phi cos theta, right? Oh, phi sin theta, I mean. So this over here between phi and z, between rho and z is phi. So find sin theta is this, and then cos theta of that gives the x value. Find rho, I keep saying phi, rho sin theta is this, and then I keep getting confused. Rho sin phi is this, and then sin theta of that gives the y value, and then rho cos phi would give the c value. In spherical coordinates, surfaces of the form rho is equal to c are spheres of radius rho. Surfaces of the form theta is equal to c are half planes at angle theta from the x-axis. Surfaces from phi is equal to c are half cones at angle phi from the z-axis. Plot the point with spherical coordinate and express its location in both rectangular and cylindrical coordinates. Okay. The part about cylindrical coordinates is the phi. It's from the z angle. I used to think it's from the xy plane. So we have example 2.63. Example 2.63. 8 pi over 3 and pi over 6. This is a point in the spherical coordinate, and in the spherical coordinate we have this, 90, we have phi, and we have theta. And in the, so we have rho. Rho looks a lot like P. They should have used some other symbol. Maybe I should start from here. Yeah, I think that's better. Rho theta phi, right? Theta phi. And then we have r theta z. And then we have x, y, z. So what should we change it into first? Express its location in both rectangular and cylindrical coordinates. So z is equal to rho. This is rho. We have, I keep getting confused. Rho cos theta is this. Rho cos phi, I mean. Rho cos phi. So z, so this is equal to 8 times 8 cos what? Pi over 6. 6.93. Then we have theta is the same in both. We have r is equal to rho sine phi. Sine phi gives the opposite one, right? So 8 sine, why is this? 3. 6.93. Did it update? And then x is, we take r cos theta. So cos, wait, no, this is wrong. E sine phi, phi is pi over 6. And then we do, hold on, sine pi over 6 is 4. Then we do 4 times cos theta. 4 times this times cos pi over 3, which is 2. And then y is r sine theta, which is 3.46. So let's see, x is 2, y is 2 root 3, z is 6.93. Okay. You have 4, you have theta and 4 root 3. Wait, let me just check. How do I get the answer in like with the root? Is this? No. So 4 square root 3, 6.93, which is z. Yeah, it's correct. Identifying surfaces in the spherical coordinate system. Describe the surfaces with the given spherical equation. So theta is equal to pi over 3. So theta is here. With that, if we have an angle of pi over 3, there will be a plane in this direction for infinity r, for r from 0 to infinity, and the entire z axis. But shouldn't the plane, why a half plane? Shouldn't the plane go in to the other side as well? Because r can be minus phi. Wait, do they allow r to be negative? Where is it? If they don't allow r to be negative, then it would make sense. But like I remember in the previous chapter, uh, we had r as negative sometimes. Okay, so this identifies the half plane. Phi is 5 pi over 6. So if we have an angle with 5 pi over 6. Z is allowed to vary, and theta is allowed to vary. I'm saying Z. Uh, Rho is allowed to vary and theta is allowed to vary. Then we will have a cone with angle 5 pi over 6. Yeah. Wait, would it be in the negative direction? Yeah. Hold on. These points form a half cone because there is only one value for phi that is measured from the positive z-axis. We do not get the full cone with two pieces. Where why though? So we have phi here. Uh, why couldn't it be? Why is it downwards though? So what is 5 pi over 6 and hold on. 5 pi over 6. 5 pi over 6 times 180 by 2 pi. 75. So we are talking about 75 degrees. Wait, I did 2 pi. It's only supposed to be pi. 150 degrees. I guess from the positive z-axis, if we do 150 degrees, we get here. I think they marked the inside. They should have marked the outside. Hold on, what are they doing here? So we have rho is equal to 6. So we have rho is equal to 6. And phi and theta are allowed to vary. So then we have what get a sphere. Where is it? Sphere. What are they doing here? To find the equation of rectangular coordinates, we use the equation phi is equal to r cos z over square root x square plus y square plus z square. I'm guessing this is the equation of this. I mean this. And the last one describes a sphere centered at 0, half, and 0 with radius half. Spherical coordinates are useful in analyzing systems that have some degree of symmetry about a point, such as the volume of a space inside a domed stadium or wind speed in a planet's atmosphere. A sphere that has Cartesian equation x squared plus y squared plus z squared is equal to c squared has simple equation rho is equal to c in spherical coordinates. In geography, latitude and longitude are used to describe location on Earth's surface, as shown in figure 2.104. Although the shape of Earth is not a perfect sphere, we use spherical coordinates to communicate the location of points on Earth. Let's assume Earth has a sphere. Earth has a shape of a sphere with radius 4,000 miles. We express angle measures in degrees rather than radians because latitude and longitude are measured in degrees. Cylindrical and spherical coordinates give us the flexibility to select a coordinate system appropriate to the problem at hand. A thoughtful choice of the coordinate system can make a problem much easier to solve, whereas a poor choice can lead an unsuccessful complex calculation, unnecessary complex calculations. In each of the following situations, we determine which coordinate system is most appropriate and describe how we would orient the coordinate axis. There could be more than one right answer for how the axis should be oriented, but we select an orientation that makes sense in the context of the problem. Note there is not enough information to set up or solve this problem. We simply select the coordinate system. So find the center of gravity of a bowling ball. We can use a spherical coordinate system. Determine the velocity of a submarine subjected on an ocean current. I guess we can use we only need like XY plane, right? Subjected in an ocean current. I think the cylindrical system would be better. Calculate the pressure in a conical water tank. I think the cylindrical one would be better. Determine the amount of leather required to make a football. I think the cylindrical one would be better. Oh, find the volume of oil flowing through a pipeline. I think over here the cylindrical one would be better. Is the spherical one only useful in sphere related problems? Clearly, a bowling ball is a sphere, so spherical coordinates would probably work best here. The origin should be located at the physical center of the ball. A submarine generally moves in a straight line. There is no rotation or spherical symmetry that applies in this situation, so rectangular coordinates are a good choice. A cone has several kinds of symmetry. In cylindrical coordinates, a cone is represented by the equation z is equal to kr, where k is constant. Spherical coordinates, we have seen that surfaces of the form phi is equal to c are half cones. Last, in rectangular coordinates, elliptic cones are quadratic surfaces and can be represented by equations of the form z square is equal to x square over a square plus y square over b square. In this case, we could choose any of the three. However, the equation for the surface is more complicated in rectangular coordinates than in the other system. In addition, we are talking about a water tank. The depth of the water might come into play at some point in our calculation, so it might be nice to have a component that represents the height and depth directly. Based on this reasoning, cylindrical coordinates might be the best choice. A pipeline is a cylinder, so a cylinder coordinate would be the best choice. A football has rotational symmetry about the central axis. Cylindrical coordinate would work best. Yeah, what happens if you choose like a spherical coordinate system? But theta is like it's like a sphere, but I think theta is like a bit larger. Wait, hold on. How do you define it? Uh, Spherical coordinate here. Is there a way to do this? If I do uh, phi is equal to pi. No, never mind. Wait, hold on. Okay. So if someone knows how to like use the other coordinate system, or if there's any other app that does 3D graph with the other system, it would be appreciated. So section 2.7 exercises. Let's see if there's any of these I want to do on stream. For the following exercises, find the most suitable system of coordinates to describe the solids. So let's do, in the answer key, we have only odd ones, right? So a solid situated in the first octant with a vertex at the origin and enclosed by a cube of edge length a, where a is more than 0. A solid situated in the first octant, so there's only one part to consider. Question 414. Question 411 actually. So we have, they said first octant. And they said with a vertex at the origin and enclosed by a cube of edge length a. What's the shape of the solid? So the vertex is here on at the center and enclosed by a cube with edge length a. Wouldn't a rectangular system be better? Let's see. Question 411. Cartesian system. Cartesian system is the rectangular one, right? Okay, that's the end of the chapter. This part was like these two chapters were very different from vectors. I thought they would relate vectors over here. I think I should just do vector valued function and curve spaces. How long is this chapter? Let's go to page 10. Vector valued function introduction. Let's just do 3.1 and then I will end the stream. Okay, introduction. In 1705, using Sir Isaac Newton's new laws of motion, the astronomer Edmund Halley made a prediction. He stated that comets that had appeared in 1531, 1607, and 1682 were actually the same comet and it would reappear in 1758. Halley was proved to be correct, although he did not live to see it. However, the comet was later named in his honor. Halley's comet will appear again in 2061. Halley's comet follows an elliptical path. It hold on. Okay. So it appeared again in 1986 and will appear again in 2061. Halley's comet follows an elliptical path through the solar system, with the sun appearing at one focus of the ellipse. The motion is predicted by Johannes Kepler's first law of planetary motion, which we briefly mentioned in the introduction to parametric equations and polar coordinates. Our study of vector valued functions combine the combines ideas from our earlier examination of single variable calculus with our description of vectors in three dimensions from the preceding chapter. In this section, we extend concepts from earlier chapters and also examine new ideas concerning curves in three-dimensional space. These definitions and theorems supported by the presentation of material in the rest of this chapter, also in the remaining chapters of the text. So definition: a vector valued function is a function of the form Rt is equal to Fti plus Gtj, or in three dimensions. Rt is Fti plus Gtj plus Hdk, where component functions are real valued functions of the parameter t. Vector valued functions are also written in this form. The parameter t can lie between two real numbers a and b. Another possibility is that the value of t might take on all real numbers. Last, the component functions themselves may have domain restrictions that enforce restrictions on the value of t. You often see t as a parameter because t can represent time. For each of the following vector valued function, the solution is right here. Do any of these functions have domain restriction? So Rt is for cos t. Sin t and cos t have domain restriction. No, actually they don't. To calculate each of the function values, substitute the appropriate value t into the function. Right, we are left with 4i. To determine whether this function, wait, okay. To determine whether this function has any domain restrictions, wait, consider the component functions separately. The first component, f of t is equal to 4 cos t. The second component, j of t is equal to 3 sin t. Neither of these functions have domain restriction. Yeah. For the second one, tan t and sec t, what's the restriction of secant theta? Secant theta. Let's just do secant x. Is there any restriction? There are restrictions, right? I think when we have a circle and then we have, if we have a unit circle, so theta, if we have a tangent, secant would define this, tangent would define this. So where is this not defined? We have t here. So if we have t as 90 degrees, then it won't be defined. Similarly, if it's like t is over here, 270 degrees, then it won't be defined. So in those cases, in pi over 2 and 3 pi over 2 and multiple of those, that's where sec theta and tan theta is not defined. So that's where the domain is restricted. The first two functions are not defined for odd multiples of pi over 2. So the function is not defined for all multiples of pi over 2. Graphing vector valued functions. Recall that a point vector consists of two quantities, direction and magnitude. Given any point in the plane, If we move in a specific direction for a specific distance, we arrive at a second point. This represents the terminal point of the vector. We calculate the components of the vector by subtracting the coordinates of the initial point from the coordinates of the terminal point. A vector is considered to be in standard position if the initial point is located at the origin. When graphing a vector valued function, we typically graph the vector in the domain of the function in standard position, because doing so guarantees the uniqueness of the graph. This convention applies to the graph of three-dimensional vector valued functions as well. The graph of the vector valued function of the form rt is equal to fti plus gtj consists of the set of all trt, and the path it traces is called a plane curve. The function of the vector valued function of the form of this form consists of the set of all trt, and the path it traces is called a space curve. Any representation of a plane curve or space curve using vector valued function is called a vector parameterization of the curve. So here they have rt is equal to 4 cos t plus 3 sin tj. We can graph it here. So delete. Is there a shortcut to delete? So 4 x is equal to 4. Actually, no. No, I don't think it would work here. If anyone knows how to graph like parametric equation, then let me know. The graph of this curve is also an ellipse centered at the origin. The values then repeat themselves, except for the fact that the coefficient of k is always increasing. Oh, so they're graphing 4 cos t I plus 4 sin t I plus tk. Oh, so then you have a spiral. You may notice the graphs in paths A and B are identical. This happens because the function describing curve P is a so-called reparameterization of the function describing a curve A. In fact, any curve has an infinite number of reparameterization. For example, we can replace t with 2t in any of the three previous curves without changing the shape of the curve. The interval over which t is defined may change, but that is all. We return to this idea later in this chapter when we study arc length parameterization. As I mentioned, the name of the shapes and curves of the graph in example 3.2c 3.2c is a helix. Oh, this is a helix. The curve resembles a spring with a circular cross section looking down along the z-axis. It is possible for a helix to be elliptical in cross section as well. For example, the vector valued function rt is equal to 4 cos t plus 3 sin t, or the coefficient over here is different now, describes an elliptical helix. At this point, you may notice a similarity between vector valued function and parameterized curves. Indeed, a given vector valued function, we can define x is equal to ft and y is equal to gt if a restriction exists on the values of t. then this restriction is enforced on the parameter. The graph of the parameterized function would then agree with the graph of the vector valued function. Okay, wait, let me see. So when t is equal to 4 pi, rt is defined as 4 cos pi over t plus 3 sin pi over t. So wait, they're defining the direction as, like, if t increases, in what direction would rt move? Is that how they're defining the direction? We now take a look at the limit of a vector valued function. This is important to understand to study calculus of vector valued function. A vector valued function R approaches the limit L as t approaches A, written like this. So RT approaches L. This is a rigorous definition of the limit of a vector valued function. In practice, we use the following theorem. So limit, you can add them. Evaluating the limit of a vector valued function. So we have RT is equal to t square minus 3t plus 4. So as t goes to 3, right? So 3 square is 9. 9 minus 9 is 0. We are left with 4i. And then over here we have 12 plus 3, which is 15j. Yeah, 4i plus 15j. Let f, g, and h be functions of t. Then the vector valued function rt is equal to fti plus gtj is continuous at point t is equal to a, if the following three conditions hold. So Ra exists, limit of Rt as t approaches A exists, and limit and Rt as t approaches A is equal to Ra. Is there a left and right limit, like when it's coming from lesser t and higher t? Similarly, the vector valued function Rt is continuous at point t is equal to A if the following three conditions hold. So Ra exists. Oh, this is basically for 3 dimensions. That's the chapter. So the question. Okay, I will end the stream here then. I need to get a better understanding about those shapes, those ellipsoids. That part is a little confusing. Okay, I will end the stream here. And I guess I will see you guys next time. Bye.